we will now describe the path of a light ray in a uniaxial crystal using Huygen's principle of secondary wavelets. Let me recollect that quickly. Supposing I have a wavefront, each point on the wavefront emits light, which, considering an isotropic medium, say this is at some time t of spherical waves coming from there for a isotropic crystal. This is a distance v delta t, and the envelope that I get of this would be the new wavefront, and the vector which will come perpendicular to that will be the k the vector that will come will be the k of the wave. In the case of isotropic medium, the ray velocity and the wave velocity coincide. Let's see what happens for a uniaxial crystal. So we start with optic axis along the simplest case, epsilon 3. Optic axis also coincides with it, eta 3. And let me have a wave normally incident. So I have here points, several points. Given this, both the polarizations will come out in the same way. So I will have here C by NO delta T, and the wave vector will be, ray vector will be also in the same direction. This is the way I will get, because this will be my wavelets and this is the tangent envelope to it. This distance is v delta t. The radius of this is C by N0 delta t. Let's consider the optic axis along epsilon 1, eta 3, and it is, my wave is moving this way. If the E2 is in that direction, that will have something like that. Whereas if E2 were in that direction, the velocity will be like that. I'm always assuming VE is smaller than VO, so that will be the wavefront. Both of them will be in the same direction, but there will be two different polarizations. This one will be polarized along epsilon 2 and that will be polarized along epsilon 1. All this we have seen. Now let us do the analysis for the case when the optic axis is making an angle alpha with respect to the third axis. Light ray is coming in this direction, light ray is coming like that. How will the wavelets be? The wavelets for the first case, the one, this is my epsilon 1, for which is polarized in the direction epsilon 2, will have a velocity v2, which will be given by some curve like that. This is my VO. On the other hand, it is here that I have my, I've drawn it rather okay. This is too big. Let me make it shorter. Like that. On the other hand, if the polarization was in that direction, that will emit a wavelet which will be given by the following ellipsoid. Now I do the same thing here. This would be, notice, if this were polarized in that direction, D is in that direction, so that will be my K wave. But the envelope now is this, and this will be the direction of the ray. This angle is beta, the angle I defined in the last lecture, which is given by E dot cos beta. One of your homework exercises, next one would be to draw the equation for these, draw the envelope, write the equation for the envelope, and show that the envelope which will lie, will be parallel to the E1 axis, will satisfy this equation for the K ray. I will give you the details associated with the problem, make it more specific. This is very well explained in the book of E.A. Jenkins, one which I have already quoted, and H.E. White, Fundamentals of Optics, section 26.2, pages 546, 549. Please read this, make sure you understand all the statements made there, and you will be able to figure out the maths. He has not written down the maths. Maths is something which we have already figured out, except for this statement here. So we stop.